Hi everybody, I hope you're doing well. Welcome back to our first Zoom lecture. This will be fun. So right off the gate, I want to just let everyone know about a little change. This beautiful PowerPoint that I have made yet again is only going to be, I'm not going to be posting it straight to Canvas like I have done in the past. From now on, since I will be posting these videos, you'll just see the PowerPoint within the videos. And then that'll maybe get you to hopefully watch it, because I know sometimes with online learning, we don't always watch everything, but that's okay. So first I want to remind everyone about some due dates coming up. So Monday, March 30th at midnight, your preliminary project is going to be due. So make sure that you have everything turned in by then. Fair warning, I do work Mondays. So if you have questions about your project that you want to email me about, I would preferably do it over the weekend or before Monday, because there's no telling how long it'll take me to get back to you on Monday, that day that it's due. So just fair warning to everyone, maybe try and get a step ahead of that and don't wait till the last minute on Monday. Next, your quiz is going to be released tomorrow on Saturday, March the 28th, and then it will be due the following Thursday, which is April 2nd, at midnight again. So you will have 30 minutes to complete this quiz, and you'll be able to have 2 attempts at it. So if you have any questions about any of that, please feel free to email me. Thank you to all the people who have emailed me before. We'll just have to be really on top of our communication going further in the class, because we're all going to do great and amazing stuff. So there's your encouragement of the day. So when we are looking at comparing multiple proportions, we are going to be using this data set again, which we used from Lab 7, if you remember, when we were doing our 1 proportion z-tests. We're just using the Johns Hopkins vaccine data again, and its use of Gardasil. So I just want everyone to remember to set your working directory to make sure you just have your file path and end on the folder that contains all your data sets. And then when you're reading in your Gardasil data, name it to whatever you want to name it, and then make sure, especially because Gardasil again is a .txt file, make sure you're using the read.table function, because otherwise it's not going to import. I've seen some of you still using read.csvs for this one, like our last quiz. So I just want to remind everyone again that you need to use the read.table function for this to import correctly. And then as always, you should always be putting in your header equals true statement so everything is aligned perfectly and everything makes sense. And then forewarning, for the rest of the PowerPoint presentation, because I just copy and pasted this from the last one, I actually named mine as just GARD instead of Gardasil, so don't get too confused on that. It's just me being different. So if we had a question that was asking whether the completion rate varied by age group, we would look at the age group data variable, which has 2 levels to it. The first level being the 11 to 17-year-old, which is represented by a 0, and the next one being the 18 to 26-year-old, which is represented with a 1. And then, so this is going to be our explanatory variable. I hope everyone's very familiar with what is an explanatory variable versus a response variable. And then our response variable, of course, is like our completed, so it's whether or not they completed the Gardasil vaccine. So you can have your 0 equals no, they did not complete the 3-shot sequence, or 1 of being yes, they did complete the 3-shot sequence. So explanatory, response. So when we're comparing categorical variables, there are 2 different ways that we can write out our null and alternative hypotheses. So the first way is similar to what you've seen before in last week with the P1 equals P2, where these are just represented, I've just represented by proportions. So we're saying that the P1 is equal to the proportion of girls aged 11 to 17 years old who completed the Gardasil vaccine. And then P2 is the proportion of girls aged 18 to 26 who completed the Gardasil vaccine. So in this case, we're interested in the age group and then the yes column of the completed or not. So that is that first way of how we interpret that. And then for the second one, this is basically saying the same thing. So this says, you know how P1 equal to P2 means that there's no difference between the 2, and P1 does not equal P2 means that there is a difference between the 2. The null and alternative here do the same thing. So theoretically, if you subtracted P1 from P2 and it was equal to 0, that would mean there is no difference between them. Whereas if you subtracted them and it did not equal 0, that would indicate that there is a difference. So both are saying the same thing, which is why they're interchangeable. But just note they're used in sets, so just be consistent. If you're going to use this set, use this set. If you're going to use this set, use this set. Just be consistent in that way. So moving on to our two proportions z-test. Whenever we're doing anything with proportions, we always want to start with our descriptive statistics. So this is just verifying that like what we're doing in R is what we're intended to doing, and then like all that stuff. So the first thing that we would do is create a frequency table. So again, whenever you're doing tables, make sure that this first variable that you're putting in is age group, which is your explanatory variable. So you would want your explanatory variable followed by your response variable. Makes sense. This explains this. Think of it that way if you need to. But this order is very important to make sure that the way we interpret this at the end is similar, because otherwise you would have to interpret it a different way, which may be a little bit harder for some of you. So order is always important and good to know. So you can view your table and then add your margins. So this is the table that we get whenever we do this. So you have your age group here in the rows, which is your explanatory variable, and then you have your no and yes of the completion, which is your response variable. And then basically right here is what we're interested in. So of 11 to 17-year-olds, 247 of them did complete it out of 701. And then of 18 to 26-year-olds, 222 completed Gardasil out of a total sum of 712 18 to 26-year-olds. So if we wanted to see the proportions of these age groups completion, we would do our prop.table, throw in that table that we made in the previous slide, and then set our margin equal to run, because this indicates that we want our row proportions, which basically means that these should add across the rows to equal 1. So 65 plus 35 is 1, 68 plus 32 is 1, roughly. You see what I mean? Rounding differently, it'd be 69 and 31. But so what this tells us is that among those girls who were 11 to 17-year-old, 35.2% of them did complete it. Whereas from this 18 to 26-year-old girls, 31.2% completed Gardasil. So they said yes to completing. So this is when we're actually going to start running our z-tests. So we will use this prop.test function again like we used last week, but then this time we're just going to concatenate and then put 247 and 222, which is the number of participants that completed the vaccination sequence in each group, which we found again from 247, 222. And then we're going to concatenate 701 and 712, which is just your total number of study participants in each group. And then you just want to, again, make sure that your order is consistent. So 247 out of 701, 222 out of 712. So just make sure that they match the order. And then we're going to end it with this correct equals false statement, because that suppresses our continuity correction. And it's basically just used for data with small counts just in case. So it's basically saying, like doing the handwritten, if you do this by hand, you should get the same output. So this is one way to do the two sample proportion test for the z-test. You could also just, again, throw in your contingency table right here. But there is a problem with how our contingency table is structured at the moment, because our groups of interest, the age group within the rows is perfectly fine and normal and looks great, but our columns is a little out of order, because whenever we're doing a two sample z-test, the first column should be the outcome of interest. So that is, our outcome of interest is saying that Gardasil has been completed, which is yes. So we do want yes in this first column in order for it to report the findings correctly. Because right now, if we did it without changing it, our confidence intervals would be flip-flopped, which is okay. But then also our proportions are all wrong as well. So it's giving us the proportion of people who did not complete Gardasil rather than those who did. So it's a little bit different, and we just want to make sure when we are doing this final report that we are reporting the correct things. So in order to, in order to correct this, we would want to make our yes column be the first column there. So we would just want to reorder our levels for the completed variable. So in order to do that, again, you would just make a new variable. So we're doing completed 2 right here, and we're doing our factor, the old variable, and then our levels of yes being first and no being last. And remember, since these are words, you have to put them in quotes in order for it to do it correctly. Otherwise, it will not run appropriately, and you'll get confused to be like, why isn't it running? But it's just because it needs quotes. So here we're going to make our new table. So age completion table 2. And again, we have our explanatory and then our response, our new response variable that we just relabeled as completed 2. Sorry, slip of the hand. So now if we ran that table, we would say yes in the first column, which is where it should be in order for this to work. And then if we ran this prop.test again, it is in the correct order now, going from negative 0.008 to 0.089. And then our proportions are again 35.2 and 31.2. This proportion is a good thing to use if you already did the frequency table and you know what your proportion should be. This is a good indicator whether or not your 2-sample z-test is actually finding what it is supposed to be from your research question. Okay, and again, this just makes it more interpretable and easy to read because it actually tells us those who completed the vaccine rather than those who did not. So when we are doing the conclusion, we can find the estimated difference, which is just the P1 minus P2. So we find 0.35 minus 0.31 is 0.04. So if we remember back to our alternative hypothesis, that is not equal to 0. So that is one evidence for the alternative. And then for our next one, for the confidence intervals, we find, and this is just rounded, so remember how this was negative 0.01 and then 0.09. They found they're 95% confident that the true difference of the two proportions is then the interval negative 0.01 to 0.09. And of course, if we remember about when we reject or not reject the null, having 0 as a plausible integer in our confidence interval does give us evidence that we would want to fail to reject the null hypothesis. So, and again, I find this again with our p-value of 0.11. So it's greater than 0.05. So we again would say we fail to reject the null hypothesis, and we can conclude that there is no significant difference in the proportion of 11 to 17 and 18 to 26-year-olds who completed the Gardasil vaccine. So these are all the different conclusions that we can make from that 2-proportion z-test. So if we wanted to calculate the p-value with the chi-square distribution, just so you guys remember, whenever we do these proportion tests, it always gives us our chi-squared value right here, which was 2.62. And if you wanted to find your z-score, again, you would just take the square root of 2.62. So if we looked at a chi-square test distribution, this on the side is straight from one of the PowerPoints or your book, I'm pretty sure. I think this is from 6.3 or 6.4. So it basically shows that a chi-square distribution is a very right-skewed distribution. And the one parameter that influences like the shape, center, and spread of this is your degrees of freedom, which I'm sure you guys have seen many, many times. And in the case of the chi-square test distribution, the greater your degrees of freedom, the more normal it kind of gets. So you see this blue line with degrees of freedom equal to 2. It is very, very, very right skewed. And then you have this 4 dotted line. It's still skewed, but a little bit more normal. And then you see 9 here. It's a little bit more normal. But a chi-square distribution is always going to be right skewed, basically. So, and then again, I just put in this little like formula for how you find your degrees of freedom. So you do your rows -1 times your columns -1. If we remember from this guy, it's just 2 rows, 2 columns. So the degrees of freedom is 1, and it also shows you in the table. So yeah, so our chi-squared value was 2.62 and our degrees of freedom was 1, which it confirms in here. So if we wanted to find the p-value, we can use the chi-square distribution function of p chi-square. So chi-square tests, because they're always one-tailed, we do not have to multiply this by 2 like we did in the previous labs. If you remember, there was a big thing about that. But because of the shape, we only have to find the upper tail, and we don't have to multiply it by anything, which is nice. So there's a few different ways we can do this. Because this function will by default give you the lower tail values, you have to find the complement. So there are 2 different ways that you can code for this. So the first one, you can do 1 minus, and then you would put your chi-squared value right here, which was 2.62, comma, degrees of freedom equal to 1. So you can do this first one as one way to find the complement. The other way you can do this is to do your p chi-square, your chi-square value of 2.62, your degrees of freedom equal to 1, and then you can also tell it lower dot tail equals false. So basically both of these just tell it to find the upper tail, which I tried to show with this little pink line, but it's a little hard to see because it's real little. But whenever we run these, we find that is 0.1055, which, if we remember, is the same p-value that our two sample z-test gave out. So this is basically showing that a one-tailed chi-square p-value is equivalent to a two-tailed z-test. I forgot to put chi-square right there, but that should be a one-tailed chi-square p-value. Y'all get it. So what if one of our variables had more than 2 levels? In this case, we would not be able to use a 2 proportion z-test. We would actually be using our chi-square test totally. So just as a little reminder for like what your chi-square test is, this is also again from your lecture slides in your book. So this is just the formula that you would use if you were doing this by hand. And this is just showing the observed counts minus your expected counts squared divided by your expected counts, and then you would add all of them together of however many you have. And then again, degrees of freedom again. So there are 3 conditions in order to do a chi-square test to be mindful of. That this is also from slides of your text. Again, I'm pretty sure this is 6.3 or 6.4. But the first being independence. So just saying that each case is independent from all other cases. The next one is sample size. So each scenario or cell must have at least 5 expected cases. So this is that expected right up here, which there's another way to find that numerically that I will show you on a later slide just to remind you all and how to connect this to like what you're doing by hand. And then of course your degrees of freedom must be greater than 1, which is why we would not run a chi-square test over this guy's stuff because the degree of freedom is 1. So we would not use it for this this kind of stuff that only has 2 levels in each variable. Chi-square tests are specifically for those that have greater than 2 levels in one of the variables. So the question that we're going to be looking at for a chi-square test is, does completion rate vary by insurance type? So again, we have our response variable of completed, but then now our explanatory variable has changed to insurance type, and there are 4 levels in this variable: medical assistance, private payer, hospital-based, and then military insurance. So again, you're going to want to first look at your descriptive statistics. So you'll make your table. And again, I want to reiterate that you're going to put your explanatory variable first, followed by your response variable. Very important to remember that. Also probably good to think about that in your preliminary project submission as well when you're making your tables or your graphs, in case you use the table to make any of them, you know what I mean. And then we're going to do our summary margins, and then we're going to calculate the row proportions for your proportion table. So this will give us all the proportions of those who said yes. So you have your 0.46, your 0.2, your 0.36, your 0.34. And those are all your proportions for each type of insurance. So you want to perform the chi-square test of association. One fun thing about the chi-square is that it's not so specific over the row that your completed variable is in, which is nice. It just does it automatically because it's a little bit better at it. So you do this chi-square dot test. You could either do, again, just plug in your variables, so your explanatory of insurance type and then your completed as your response. And then again, you want to make correct equals false. Or you can plug in that table that we just created as an object and then followed by correct equals false. So this is the output that you'll get whenever you do either of these tests. So it'll tell you your chi-squared value of 31.2. And then it'll give you your degrees of freedom of 3. And then your p-value, which is a very, 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 very small p-value. So the assumptions for this chi-square test, again, is that all expected cell counts are at least 5, and I included the little thing for how you find your expected counts by hand, which is just your row total times your column total divided by your table total. So you're gonna, in order to test for this assumption, you're going to save your chi-square test results into an object. So this is what we did here with insurance comp type complete test. So we had that, and then we saved it into this object, and then we wrote out this object, and then we put $expected. So this will help you view the expected cell count, which is just this formula, for each type. So we'll see here that hospital-based 27, medical assistants 91, military 109, private payer 239. So in all of these, none of them are less than 5, which is great because that means our conditions are satisfied for about inference using the chi-square test. So we got our Fisher's exact test next. So if we wanted to do something in case for one day maybe our expected cell count for one of those is actually less than 5, we would use a Fisher's exact test instead. So to do this, you would again just either input your variable names or your table into this Fisher.test function. And again, that's all you have to do for a Fisher test. And then you will get this value, which is just telling you what your p-value is. And in this case, it is still very, very small. So it's 3.432 to the negative second. So if we want to look at it in this way, because sometimes if you just look at by like the number, it'd be like, oh, 3 versus 7, that's a big difference. But in actuality, there's very, very, very little difference. It's very, very small difference between the two. Definitely not a big difference. So that is something to take into account whenever you are thinking about whether you want to use a chi-square test or not. So I think that is where we're going to end today. If you guys have any questions, please let me know and I will answer them as quickly as possible. Otherwise, good luck with your other classes and good luck on your quiz. And I look forward to hearing from you guys.